just start. So today I'll be giving a talk on quantum reservoir computing for digital health and a specific use case we worked on in collaboration with a startup from Berlin and also with QERA. And the topic was around monitoring quality of life through the voice, so through vocal biomarkers. And first of all, I want to emphasize the broad range of solutions across the whole care continuum for digital health solutions through awareness, diagnosis, and also treatment. And specifically for treatment, a key factor here is quality of life, because we want to adapt the treatment to the personal patient needs of patients. And in this case, we really have to know or to be able to assess the quality of life. But that's a really hard task, because quality of life is a complex, multidimensional concept. You can imagine the physical dimension, the psychological dimension, then also the social dimension, and there are also more dimensions that play a role in quality of life. So it's really a multidimensional concept. And nowadays, the way they measure quality of life is through questionnaires. So the patient fills out a questionnaire with disease-specific or not disease-specific questions, and then a quality of life score is calculated. And they do that every 2 weeks or every month. And the problem or the challenge here is that we have no insight about the patient between these measurements. So it's time points. And we want to go into the direction of a more continuous monitoring of quality of life, and also a more objective monitoring of quality of life than these self questionnaires. And therefore, we need a medium or something that can measure these this complex concept. And a great medium for this is actually voice, because our voice, our human voice, or the speech process is very complex. It involves a lot of systems like the respiratory system, the lungs, the muscles around your mouth area, and the brain, of course, which coordinates everything. And if one of these systems is affected by a disease, for example, this has a direct influence on the way people talk. So voice changes can then reflect the health status of the physical and mental state. And these vocal features are called vocal biomarkers, and can capture changes in acoustic characteristics, like, for example, pitch, loudness, tone. And these vocal biomarkers are linked to a few diseases, basically these diseases that can influence the systems I mentioned before. For example, neurological diseases, mental diseases, or respiratory diseases. And we want to use these vocal biomarkers to assess quality of life for a personalized treatment, so to have the patient in the center. And for that sake, we need a data set, so a data collection and preparation of the data set with these vocal characteristics or vocal features. And we want to do a machine learning analysis with these vocal features. But because quality of life is such a complex concept and multidimensional concept that it's really hard to measure, and voice in itself is a very complex medium, we have a really complex data structure here. And for that sake, we explore the application of quantum reservoir computing to deal with this complexity, with these complex data, to maybe gain an advantage over classical methods. And for that quantum part, we work together with QERA for the QRC part. And for the data and the data preparation, we work together in collaboration with a startup from Berlin, It's called peak profiling, and they are specialized on disease detection through the voice. So let's give you a few information about the data set we worked with. It was a large data set of more than 8,000 data points. And the data were audio recordings where the patient did a task, for example, free speech or picture description, counting tasks, or there are different tasks the patients did. And then the label was the quality of life score of the questionnaire. So the patient did one task, so he spoke into a microphone and then filled out a questionnaire. So we have a data and the label. So it's a supervised machine learning task. Now for the features, we work here with two different data sets. One data set was a musicological feature set. So these features were extracted from a lot of musicological groups, let's say. And we dealt with a lot of features, so in overall over 1,400. And because we work here with simulations of QRC, we were limited, of course, in our feature dimension in 16 features. So we had to reduce our features in this case, and therefore we reduced every musicological group into a feature, and then we ended up with 17 groups, and then we did a SHAP analysis to calculate the feature importance of each feature, and then selected the 16 most important features there. Then we explored also a different data set, and this one was specifically engineered from the startup from Peak Profiling. And they introduced their specific knowledge, and these features did multiple interactions, and they contained really more information. So this data set is more informative and complexer than the other one. And for this sake, we also did the SHAP method to reduce the features from overall 180 in this data set to also 16 features, so the 16 most important features for our machine learning and QRC analysis. Our machine learning models used in this project were 6 overall, with also different complexity and different size. We used 2 neural networks, one smaller, a 3-layer neural network, and one bigger with a 5-layer neural networks. Then we used 2 support vector machines, one linear support vector machine and one with an RBF kernel, and then also one random forest model and one KNN classifier. So now for the QRC part, I want to motivate the topic from the reservoir part, so reservoir computing in general. So in general, you have a pre-processing step where you do your classical pre-processing, like in the normal machine learning pipeline. And then you have a reservoir that its dynamic is directly influenced by the input parameters, so by the features you give into the QRC. And then you measure the dynamic of the system, so the dynamic of the reservoir, and these measurements are then the input for your post-processing. And in the post-processing, you then have a machine learning model like before, for example, a neural network that does your prediction. And in this case, we used quantum reservoir computing. So we did our pre-processing like before, the same classical pre-processing steps. And then we need to encode our data into the quantum system. So in our case, we used 16 features, so also a 16-qubit system. And the encoding was done by encoding it into the parameters of the Hamiltonian. And we used here local encoding. So each feature was encoded into a qubit. So we had a 16 qubit system where each qubit represented to one feature, for example, loudness or pitch or whatever. And then after doing the encoding, so we have our quantum system, we let the system evolve. and we probe that system several times in successive time steps. And we do that by doing a measurement or basically doing a lot of measurements and getting these expectation values. And these expectation values are then the input for our post-processing. So we have the dynamic of our system. We probe that several times. We get our expectation values, and we feed these quantum embeddings, the expectation values, into the post-processing, so into our machine learning models. And for this analysis, I have to say it was a proof of concept project, so it was a binary classification. So we had our initial quality of life score, and a threshold was chosen, and every quality of life score that's over that threshold was labeled as quality of life high, and every threshold that was under that was labeled as quality of life low. So we did our analysis. And we see here that in general, we got really good results. We got our best performing model, our KNN. So I have to say, this is the analysis with the basic musicological feature set. We got our best model in a KNN with a F1 score of nearly 80%. And we see that the QRC models are in orange, and the machine learning models are in blue. And we see that the QRC models performs very similar to the machine learning models, but we do not really gain an advantage with QRC with this data set. But overall, very strong and balanced performance. And then for our analysis with the deep dive feature set, so here with the more complex features, we actually see an advantage with QRC. So here the orange bars are higher than the blue, and specifically our best performing model is a QRC KNN model. And you can see here that the overall performance is a bit lower than with the other feature set. And I have to say that this was on a subset of the whole feature set. So it was not all 80,000 data points used here, just 1,200. That's why the overall accuracy or F1 score is a bit lower. But this is a very promising result to see that we can gain an advantage with quantum reservoir computing with more complex data. And this is really something we could use going forward. Specifically, reservoir computing in general and quantum reservoir computing, because on our, let's say, on our current hardware or in the NISQ era, where we have to deal with a lot of noise and a lot of variational algorithms hit its limit, because we cannot train a million parameters or update or optimize a million parameters or a billion like we can do with AI models. Therefore, in quantum reservoir computing, we have this huge advantage that we do our training in our post-processing step. So we do not train our quantum reservoir in this pipeline. We do our training in the post-processing and in the classical part. And there we are good. We can do a good classical training there. So I think this is really a promising field, and this is also, let's say, our key findings, that we really demonstrated that it is feasible to assess the quality of life of a patient through the voice. We got strong results there. And regarding the quantum reservoir computing part, we saw, first of all, that with, let's say, simpler classifiers, we get better results with quantum reservoir computing. That's also kind of intuitive. But with more complex or more informative features, we can really gain an advantage with quantum reservoir computing. And I think that is one field where in the near term, in the future, we can really see some applications, not only in healthcare, but in a lot of industries. And with that, thank you very much for your attention.
Thanks, Michael, for the great talk.
Yes.
We have time for our questions.
So great results. So what do you think is behind the improved accuracy? What is really changing in your feature space?
So why we gain this advantage, basically?
Yes, is it a sort of a quantum phenomena, or what's behind it really?
So QRC is basically a transformation of your input dimension in a much higher, or a nonlinear transformation in a much higher dimensional space. And the idea is that with that transformation it's like you blow up your feature space, and you can detect some patterns that you could not detect before. So this is really a dynamic that is very sensitive to the input features, and you can enhance these complex patterns, basically, that you could not do classically. So these evolvement of the system of the quantum reservoir you cannot do classically, and with that transformation in this high dimensional space you gain these insights about these complex patterns.
Okay, thank you.
Yes.
Thank you very much for your results. Maybe it's following a little bit the questions, because just to be sure to understand, what you did is you have like the let's say the pre-processing step when you're transforming the data with like your number of features. Then you have the quantum reservoir computing, which is sort of massaging the data to transform it into another way of representing the features, and then you feed that in your classifier at the end, which is classical machine learning, correct?
Correct, yes.
Now I'm wondering, because you have added another layer in your pipeline, which is the quantum reservoir computing, but you could also have used classical reservoir computing, which would also have changed the pipeline. And then I'm curious about what would have been the results with classical computing, because right now I'm not sure the result you have, it's because of quantum. It's made just because you have massaged the data in different way, because you're comparing with or without these steps. So if you don't compare to classical reservoir computing, I'm not sure you can claim what you see it's because of quantum. It's just because you are massaging the data in different way.
That's actually an excellent question, and you're totally right. And we also dig into it, and there will be coming out a paper which also includes classical reservoir computing. I did not include it here for this analysis, but we also analyzed it with classical reservoir computing. So the guys from Cura know this method. Basically, it's the same method, but without the quantum part. So the classical part, you set the spin to infinity, and then you calculate your classical reservoir computing. And we did that, and we saw that we gained there also a quantum advantage over that classical reservoir computing part. And that's, you talked about it, that it is very important to compare, basically to have a fair comparison of the results. And this is one point that will be then included into the paper that I did not include here because the final results are not ready there. But it's a fair point to compare really the reservoir with quantum reservoir to see that the quantum advantage is really quantum and not the reservoir in general.
Thanks. Yep. That's important indeed.
Yes, thank you very much.
Thank you. Is it possible to try on other quantum paradigm, like maybe gate-based or photonics?
There are also other approaches. In this case, we worked with squares or neural atoms, but there are also quantum reservoirs based on other approaches. For example, gate-based. There is, for example, on IBM hardware, you can run it on gate-based, and very effective here is something called mid-circuit measurement. You can use to really have a memory and use that for a quantum reservoir. So also other modalities you could use for quantum reservoir. Neutral atoms are just one, but in this case, one really effective one.
Okay, thank you.
Yes.